We're going to start talking about the notion of an inverse function. So this definition definitely looks fairly technical. Basically, if we have an injective or a one-to-one function f of x, we can define specific to that f an inverse function, which we'll usually denote by f with a raised -1. And it's not a power of -1, it just means like go backwards. But we can define this inverse function. And so that here's where it looks a little bit technical. F composed with f to the -1 of x is just x, and f to the -1 composed with f of x is just x. So what we're actually getting here is that the composition just sort of gives you this inverse, sorry, not inverse, identity mapping where x just maps right back to itself. So the idea is here, f is going to map x to some y value, but then the inverse function is going to undo that action, and it's going to map your y straight back to x. And because the function is one-to-one, there's only one x that mapped to that particular y, so we know exactly where to send y back to. So it actually creates a nice new function for us. Yeah, so that's the idea. So essentially the idea is, it just like, it undoes the actions. Anytime you do any sort of equation solving, what you're actually doing is applying inverses. So even something as simple as like the equation x plus 3 equals 5. So for solving an equation, what we're trying to do is isolate x, and we do that by applying inverse operations to get x on its own. So the desired output is just an x. So what we'd want to do is apply the inverse to adding 3, and that would be subtracting 3 to both sides, and then we actually end up with x is 2. So it's the very basic element of equation solving is actually applying inverse functions, and that's how we'll actually use it throughout the rest of this course with other functions that we'll introduce. So just as a first example, we're going to have g of x and h of x. They're two linear functions, and what we'll see is that they're actually inverses. So the test that we can use if we follow that definition is that if we do a composition of the functions, we just get the identity. We just get x back out. So we'll check that. So what I'm going to do is check g composed with h and h composed with g. So g composed with h of x is g of h of x is g of 1/3 x plus 2. And I'm going to plug that into my g. So that would be 3 times 1/3 x plus 2 minus 6. And I'm going to distribute the 3 through. So 3 times 1/3 is 1. Plus 6 minus 6. And so we just get x. That's exactly what we want for that output. And then similarly, I'll do the same thing the other way around. And it should work. And so I'm going to get h of 3x minus 6 is, so I'm going to plug that in where the x is. So I'm going to get 1/3, and instead of x, 3x minus 6, and then plus 2, and distribute the third. So 1/3 times 3 again is 1. 1/3 times -6 will be minus 2 plus 2. So we actually just get x. So whatever happens to this x, the inside function maps it to something else, but the outside function sends it right back to x in both cases. So these are inverses. If you wanted to write it out a little bit more technically, we could actually write that h of x is g to the -1 of x, the inverse of g, and g of x is h to the -1 of x, so the inverse of h. And note that g to the -1 of x, so that is this h of x function, 1/3 x plus 2, it's not the same thing at all as g of x to the -1, which would be 3x minus 6 to the -1, which is like a reciprocal function, right? It's not the same thing. So the notation is very, very different. They don't mean the same thing at all. The placement of that -1 is going to be really important. All right, I'll just do one more example. Okay, we're going to explain why f of x is x squared and g of x is root x are not inverses. All right, so I mentioned before that we use inverses to solve equations, and if I have an equation x squared equals something, I definitely use a square root to solve that equation, but they're not going to work perfectly together. One thing that we could actually look at is if I actually do, let's say, f composed with g. So if I look at this, that'll be f of g of x. So that'll be f of root x, which is root x squared. So that actually is just x. So that much is true, but where we're going to actually run into a little bit of a problem. Sorry, I'm just writing the same thing. So we're going to run a little problem if we actually try to plug f into g. So that is the root of x squared. So that is actually not x. That might look like x, but it's not. I'll give you an example why. If we have a look at, let's say, the square root of -3 squared, right? That's not -3. It's not the input. It's actually going to be the root of 9. And the root, it's a function. It only takes you to the positive one. It always takes you to the positive output, and it's 3. So it's actually not the same thing. What we actually get is always the positive version of that answer. It's actually an absolute value. So what we actually get for that is not quite x. It's the absolute value of x. It's not, so if we plug in a negative value, we don't get the same output. So for that reason, it's actually they're not inverses. And in particular, if you go back and look at the definition that I wrote down, it has to be a one-to-one function. And we don't have that. So f of x equals x squared is not one-to-one. So it actually doesn't have an inverse. Be careful with that. It doesn't have a perfect inverse. So that's what we're really interested in. What we're talking about are these perfect inverses. What we have is this kind of fudgy inverse, or what you might want to call a restricted inverse. So that g of x equals root x is a, you don't really need to know this definition, but it's useful. We'll touch on this later as well. It's a restricted inverse in that it doesn't work for all values of x. It actually only works for non-negative values. And that's the restriction. So yeah, I'm not going to ask you on that, but it's useful to know that because this idea is going to come up a lot when we talk about the trigonometric functions later on. You get a lot of inverses that don't do fully what you want them to, kind of like the square root. It's just a sort of blown up version of that.